Hi friends, in this video we are going to discuss about previous gate questions in our DC machines. Let's see here. A DC series motor driving an electrical train faces a constant power load. It is running at rated speed and rated voltage. If the speed has to be brought down to, speed reduces to, brought down to 0.25 per unit. 0.25 per unit, nothing but 1 by 4th. The speed reduced to 1 by 4th. The supply voltage has to be approximately brought down to. To get this value, what about supply voltage? Approximately brought down to. Let's check it. So generally they given that is constant power load. Constant power load. P is equals to N into T. Here power is constant. So the torque is directly proportional to 1 by N. If this is constant, if torque increases, speed reduces, right? Torque inversely proportional to N. Torque inversely proportional to N. Yeah, torque inversely proportional to N. Now tell me how. Generally this is a DC series motor, that's why the torque directly proportional to Ia square also. Torque directly proportional to Ia square, torque inversely proportional to N. Here he said that speed reduced to 0.25 per unit. Nothing but torque increased to 4 per unit, right? Yes or no? Inversely proportional, right? Torque, the speed reduced to 1 by 4th per unit. 0.25 nothing but 1 by 4th per unit. So the torque is inversely proportional. So the torque should be increased to 4 per unit. Nothing but the torque is directly proportional to Ia square. If torque increased to 4 per unit, nothing but the current increased 2 per unit. If current increased 2 per unit, then torque increased 4 per unit. But I am doing in reverse. If torque increased 4 per unit, nothing but the current increased by 2 per unit. So armature current increased 2 times R2 per unit. 2 per unit. Then what happened to supply voltage? Again here power is constant, P is equals to E into I. This should be constant. If power increased by 2 times, then our voltage should be reduced to 2 times. So E is equals to V by 2 per unit, or simply 0.5 per unit. Reduced off. Here current 2 times, that's why voltage should be reduced to half. That's why the voltage reduced to half, nothing but 0.5 per unit. 0.5 per unit. The voltage should be reduced up to 0.5 per unit. What we done? Here power is directly proportional to NT. Power constant, nothing but torque inversely proportional to N. Torque directly proportional to Ia square. Speed reduced to 0.25 or 1 by 4 per unit, nothing but torque increased to 4 per unit. If torque increased to 4 per unit, nothing but the Ia increased by 2 times. If Ia increased by 2 times, the EMF should be, our back EMF should be reduced 2 times, nothing but half V by 2, nothing but 0.5 per unit. Very simple question. Let's see here. Next question, see here. The armature resistance of a permanent magnet DC motor is 0.8. Armature resistance of a permanent magnet DC motor is 0.8 ohms. 0.8 ohms. At no load it draws, at no load, Ia naught 1.5 amperes. Supply voltage 25 volts. And runs at speed of 1500 RPM. Runs at speed of 1500 RPM. 1500 RPM. The efficiency of the motor, we have to find out efficiency of the motor while it is operating on load. operating on load at 1500 rpm, drawing a current of 3.5 amperes. So the load current is 3.5 amperes, armature current or load current. Generally armature current. Same source will be. We have to find out efficiency. Right? How we can find out efficiency? Efficiency is nothing but output by input, right? Output by input. We have to find out output. Output nothing but generally the power nothing but EB into IA. At no load, its value we have to find out first. Tell me at no load what is its value? EB nothing but V minus IA into RA. V minus IA into RA. EB into IA. IA nothing but 1.5. If you calculate this, you can get 35.7 watts. 35.7 watts. If you calculate this, you can get 35.7 watts. Next, calculate the power at loaded condition. At loaded condition, EB into IA. What is EB? 25 minus 3.5 into, what is the current? IA 3.5 into armature resistance into IA 3.5. If you calculate this, then you can get 77.7 watts, the power at loaded condition. Power at no load condition, power at loaded condition. At no load condition, IA 1.5. At loaded condition, the IA 3.5. This is power at loaded, power at no load. Power at no load, nothing but the losses. Simply nothing but these are losses. Generally, these are friction and windage losses. And here, this is power at loaded condition. That's why power at loaded condition. That's why this is total output. This is total output. This is only losses. This is only losses. I want the power at shaft. The power developed at shaft. The power developed at shaft is equals to 77 minus 35. 77 minus 35, its value 42 watts. This is actually the power output of the machine. This is actually the power output of the machine. Then what is power input? Power input is equals to V into I. What is V? 25. What is I? I 3.5. This is actually power input. This is actually power input and this is the power output. Now, efficiency is equals to 42 divided by 25 into 3.5. Tell me, what is the value? 420 divided by 25 into 35. If you calculate this value, you can get 48%. You can get 48%. Then, what is our answer? This one. Option A is correct answer. What he done actually? Here armature resistance given and efficiency also we have to find out. Armature current at no load, supply voltage and the speed. Here armature current at loaded condition. At no load condition, power output nothing but the losses. No load condition, power output nothing but the losses. At normal condition, nothing but load condition, this is the total power output. So this minus this, nothing but the power at the shaft. Power at the shaft, nothing but output. And input, nothing but V into I, 25 into 3.5. Then efficiency is equals to this 42 divided by this value. You can get 48%. Yeah, this is the very simple question. Okay, next question. Let's see here. A 8-pole DC generator has 8-pole DC generator has simplex wave winding. 8-pole DC generator P is equals to 8. Simplex wave winding number of parallel paths is equals to 2. Containing 32 coils of each 6 tons. containing 32 coils of each 6 tons. The flux per pole 0.06 Webers. The machine running at 250 RPM. Then find induced EMF. Tell me, sir, induced EMF formula easy is equals to 5Zn by 60 into P by A. We have N 250, P8, A2 and flux 0.06. Now I want to find out Z. Z nothing but number of conductors. They given 32 coils each 6 tons. 32 coils each 6 tons, nothing but how many number of tons? 192 number of tons. 192 tons. But in generally, 1 ton contains 2 conductors. 1 ton contains 2 conductors. That's why 192 into 2 is 384 conductors. 384 conductors. Let's find out the generated EMF. EZ is equals to flux 0.06 into Z. 384 into speed 250 divided by 60 into P by A. 2 ones, 2 fours, 4 ones, 4 15s, 5 threes, 5 fives, 3 ones, 3 0.02. 0.02. So what is our answer finally? 0.02 into 50 into 384. What is its value? Its value 1. So 1 into 384. Finally 384 volts. 384 volts. This is our answer. Option C is our answer. 384 volts. 384 volts. This is about the question. A very simple question. E is equal to. This is very, very important here. To find the number of conductors is very important. Number of conductors. Actually, they given 32 coils, each 6 tons. 192 tons. So Z is equals to 192 into 2. 384 conductors. That is very important. I no need to cancel this because the answer is 384. Right, sir? Yeah, very easy question. Okay, next question. 2 magnetic poles revolve around a stationary armature carrying 2 coils. 2 magnetic poles revolving around a stationary armature with coils C1 and C1 dash, C2 and C2 dash. As shown in figure, consider the instant when the poles are in a position as shown. Consider the instant. This is the instant. This is the instant. Identify the correct statement regarding the polarity of the induced EMF at that instant. We have to find out the polarity of induced EMF in these four conductors. Actually, this is the axis which is called as polar axis or D axis. This is the axis which is called as Q axis. Along the Q axis, nothing but MNA axis. Along the MNA axis, there is no induced EMF. There is no induced EMF in the conductors. In C2 and C2 dash, there is no induced EMF because this is a MNA, magnetically neutral in axis. Yeah, okay. What about C1 and C1 dash? Actually, this is a pole rotating stationary armature. But we know that rotating armature. For rotating armature, we have a principles to find out the direction of induced EMF. Right hand rule. But actually here, poles are revolving, not armature. So, as per our assumption, if poles are rotating in one direction, nothing but the armature will take in opposite direction. This is our assumption. You know that actually. In theory, you can find it. Yes, if poles are rotating clockwise, nothing but if the poles are stationary, the armature rotating in anti-clockwise. You have to remember this. Now tell me, now here conductor is in upward direction, here the conductor is in downward direction. Here conductor is in upward and the flux always north to south. Flux always north to south, right? Let's see, this is my flux direction. This is my flux direction and this is my conductor direction and this is my EMF direction. Yes or no? The flux direction, the conductor direction upwards. When the rotor is rotating like this, when the rotor is rotating like this, the conductor upwards, flux direction north to south, flux direction north to south, then EMF outwards, outwards nothing but dots, outwards nothing but dots. And C1 dash, same flux direction, but the conductor direction in downwards, conductor direction in downwards, then EMF direction inwards, inwards nothing but cross, inwards nothing but cross. So here C1, the induced EMF is dot and C1 dash induced EMF is cross. Very simple question. The basic Fleming's right hand rule. Direction of induced EMF. But here you have to remember one thing. When the given poles are revolving, we have to assume the armature rotation in opposite direction. If poles stationary in this case, the rotor rotates in opposite direction. So here conductor upwards, here conductor downwards, then you can get these are the answers. Let's see here. A 50 kilowatts DC shunt motor is loaded to draw rated armature current at any given speeds, when driven at off the rated speed by armature voltage control method. And also next question, at 1.5 times the rated speed, by field control method, and then the respective output powers delivered by the motor. This is my question. Generally we know that for motors EB is equals to V minus IARA, and generally EB is equals to K into phi into N. From this, N is equals to V minus IARA by K into phi. Here we can control the speed by voltage control method, by flux control or field control method, and by armature resistance control method. Generally, when voltage reduces, speed also reduces. So, voltage control method is used for below rated speeds. And when flux decreases, the speed increases. When flux decreases, the speed increases. Nothing but the flux control method used for above rated speeds. Yes or no? See here, half the rated speed by voltage control method, 1.5 times of the rated speed by flux control method. The voltage control method below rated speeds and flux control method above rated speeds. Actually, here flux reduces, here voltage reduces, right? Generally, they given the power is in generally 50 kilowatts. Now, at this condition, respective power outputs are, that is the question. Generally, in this case, in above rated speeds, the torque is variable and power is constant. Nothing but constant power, variable torque drive. Constant power, variable torque drive. In this case, when flux reduces, torque also reduces. That's why constant power, variable torque drive. But in this case, the machine acts as a constant torque, variable power drive. Constant torque, variable power drive. In first case, This is constant torque variable power drive. We know that P is equals to N into T. I said you in below rated speeds, the machine acts as a constant torque variable power drive. Nothing but the torque is constant. When torque is constant, the power is directly proportional to N. In this first case, speed reduced to half. Speed reduced to half. So our power also reduced to half. Nothing but at this condition, the power is half of the actual value. Nothing but 25 kilowatts. This is first one. The respective power outputs in that the first one answered 25 kilowatts power output. And coming to second one, here also same P is equals to NT. And here the constant power variable torque drive. The power is constant. I told you the power is constant. Of course, torque is varying. But he asked us the respective output powers. Yeah, in this condition, the power is already constant, I told you. Then tell me, what is the power in second condition? Constant, nothing but the same power, 50 kilowatts. This is the second one. In first case, 25 kilowatts. In second case, 50 kilowatts, because this is a constant power drive. But here, the constant torque drive, then P directly proportional to N. When speed off, the power also off. Yeah, very easy question. Here you have to remember that in below rated speeds, constant torque drive. In above rated speeds, constant power drive. This is very important note here. In relation to DC machines, match the following. This is a question. Here, armature EMF E and developed torque T and developed power P. And here some are there: flux, speed, armature current, flux, speed, flux, armature current, speed, only armature current. Like that, many are there. Let's see which depends on which. Let's see. Generally, we know EMF E is directly proportional to phi into N. Yes or no? How it is, sir? Generated EMF is equals to phi Zn by 60 into P by A. From this, Z already constant, 60 constant, number of poles constant, parallel paths constant. So some constant K, phi into N, EMF is directly proportional to phi into N. Yes? So the armature EMF is directly proportional to phi into N. Phi into omega is the first one. Next, second one, developed torque. The torque is directly proportional to phi into Ia. We know that. The torque is directly proportional to phi into Ia. Where it is? The torque is directly proportional to phi into Ia. This is a very simple thing. And next one, developed power. This is the first one. And this is the second one. And third one, power. Power is equals to omega into T, right? P is equals to omega into T, right? Yeah, we know that P is equals to omega into T. T nothing but phi into Ia, right? T nothing but phi into Ia. So the power is directly proportional to omega into phi into Ia. Where it is? Omega into phi into Ia. So the third one belongs to first one. The C, power directly proportional to omega into the power directly proportional to omega and phi and Ia. This is very simple question. Yeah, we have a 3 A, B, C, D. A is very simple. E is directly proportional to phi into N. B directly proportional to T is directly proportional to phi into Ia, and C the power is equals to omega into T, we know that, and omega, okay, what about T directly proportional to phi into Ia? Is very simple question. In DC mission, which of the following statement is true? In DC mission, which of the following statements is true? Actually, they given 4 statements. In that, one of the option they given, compensating winding used to neutralize the armature reaction. Compensating winding used to neutralize the armature reaction, while interpole winding used to improve the commutation. Yeah, this is 100% correct, right? Why, sir? Generally in DC machine, we are using compensating winding here. Generally in DC machine, we are using compensating winding, which placed under pole shoes. This compensating winding used to eliminate the armature reaction, used to neutralize the armature reaction. But whereas interpolar winding, if you are using interpolar winding, this interpolar winding produces the flux. This interpolar winding produces the flux to nullifies the reactance voltage, which produced in the commutator segments. To nullifies the reactance voltage, you know the formula, reactance voltage VR is equals to minus L into 2IC by TC. Minus L into 2IC by TC, the reactance voltage, which produces sparkings at the brushes, which produces sparkings at the commutator segments due to this reactance voltage. This reactance voltage nullified by the flux which produced by the interpoles. This reactance voltage nullified by the flux which produced by this interpolar winding. So that's why the interpolar winding used to improve the commutation. So this is 100% correct answer. They given another option, reverse. How they will give you? The compensating winding used to improve the commutation, and interpolar winding used to neutralize the armature reaction. Both are used to neutralize the armature reaction. Both are used to improve the commutation. Like that, they will give you options. In that, this is 100% correct answer. Compensating winding used to neutralize the armature reaction. Interpole winding used to improve the commutation. A 220 volts DC machine supplies 20 amperes at 200 volts as a generator. Supplies 20 amperes at 200 volts as a generator. A 220 volts DC machine supplies 20 amperes at 200 volts as a generator. And next, armature resistance 0.2 ohms. If the machine is now operating as a motor at same terminal voltage, and current, at same terminal voltage and current, but flux increased by 10%. In this motor, the flux increased by 10%. The ratio of motor speed to the generator speed is what they want? The ratio of motor speed to the generator speed is. This is my question. First, we have to know the formula for this. What is the formula for this? Generally, motor speed to the generator speed is equals to, what is actual formula? N2 by N1 is equals to EB2 by EB1 into phi1 by phi2. This is actually the formula. N2 by N1 is equals to EB2 by EB1 into phi1 by phi2. Why the formula like this? Because the N is directly proportional to EB by phi. N is directly proportional to EB by phi. From this formula, Nm by Ng is equals to motor nothing but back EMF, generator nothing but generated EMF, and the flux in generator by flux in motor. Flux in generator by flux in motor. Tell me, what is the back EMF for my question? V minus IARA. What is V? 200 minus, what is IA? 20. And what is RA? 0.2. So the EB is equals to 196 volts. This is 4. 200 minus 4, 196. Tell me, what is generated EMF? EG is equals to V plus IARA, that is equals to 200 plus IARA. Then what is the value? The generated EMF EG is equals to 200 plus 4, 204. Yes? For example, 5M is equals to how much? Before that, we have to know the phi z. Phi z is equals to, for example, phi. For example, generator flux phi. But in motor, they given flux increased by 10%. In motor, flux increased by 10%. Nothing but 1.1 into phi. 1.1 into phi. This is motor flux, generated EMF, motor EMF. Then substitute in this. Then we can get the answer. Directly we can get the answer. Let's see, I'm substituting here. Nm by Nz is equals to, Nm by Nz is equals to EB 196 divided by EZ 204 multiplied by phi g. Phi g is the phi, and phi m 1.1 times of phi. Phi gets cancelled out. If you solve this one, you can get 0.87. If you solve this calculations, you can get 0.87. So this is our correct answer. So what is actually the formula? N2 by N1 is equals to E2 by E1 into phi 1 by phi 2. This is the formula actually. From this we derived this one. We wrote this one. From this I calculated back EMF and generated EMF, and they given the motor flux increased by 10%. So 1.1 into phi, where generator flux is the phi. Right? So then substitute all the values, then you can get 0.87. In DC motor, which can provide zero speed regulation at full load, which can provide zero speed regulation in full load without any controller. Be careful, without any control. With controller, we can provide in any electrical machine zero speed regulation. But without any controller, which machine provides this zero speed regulation? Tell me which of the following is correct answer. For that, I am drawing the speed and load characteristics. For example, IA and N characteristics. Even under no load condition, some speed should be there for shunt motor and compound motor is called no load speed. Even IA is equals to 0. The motor rotating at some speed is called no load speed. For example, this is no load speed. If we draw the speed characteristics for series motor, you have an idea already. I think you have an idea. For DC series motor, the speed characteristics are like this. Yes? For DC series motor speed characteristics, this zero speed regulation not possible. Next one, for DC shunt motor. For DC shunt motor, the speed characteristics are like this. Slightly drooping characteristics were called as. For series motor and for shunt motor, this is also not possible. Zero speed regulation not possible. And for cumulative compound motor, the speed characteristics are like this. Speed characteristics are like this. This is also not possible. But in differential compound motor, the speed characteristics are like this. differential compound motor, the speed characteristics are like this. See here, at no load speed and at full load speeds are same. Speed regulation, nothing but no load speed minus full load speed by no load speed, right? Here, the no load speed and full load speed both are same. If both are same, 2 gets cancelled out and speed regulation is 0. That's why the 0 speed regulation only possible in differential compound motors. Only possible in differential compound motors, and remaining all, generally, these all are positive speed regulations. But only in differential compound motor we can get the 0 speed regulation. This is linked answer question actually. This is the data for 2 questions. In that one question is there, other question I will give you. This is the data for 2 questions. What they given? They given first supply voltage of 240 volts, DC shunt motor, draws 15 amperes, nothing but the line current of 15 amperes, while supplying the rated load at speed of 80 radians per second. 80 radians per second. The armature resistance they given 0.5 ohms armature resistance, and the field winding resistance 80 ohms, right? Let's see in diagram. Let's see the data. In diagram, the data, let's see here. Generally, for example, this is my DC shunt motor. Here the supply voltage is 240 volts, and here the line current is 15 amperes. In that, this is ISH and this is IA. Generally, ISH is equals to V by RSH. Yes or no? V, what is the supply voltage? 240 volts. And the given field resistance of 80 ohms. Finally, 3 amperes current flowing here. ISH of 3 amperes. This is 15 amperes. This is 3 amperes. 15 amperes come here. In that, 3 amperes divided for field winding, and remaining IA is equals to 12 amperes. My armature current is 12 amperes. Yeah, this is our data. Now let's see the question. The net voltage across the armature resistance at time of plugging. Do you know what is the current at the time of plugging? The breaking current IAB is equals to, what is the formula? The supply voltage plus back EMF divided by armature resistance plus extra resistance. Yeah, what is the voltage now? The voltage at the time of plugging is V plus EB. Nothing but, what is V? They given 240 plus, what is EB? What is the formula for EB? V minus IR here, right? V minus IA. What is IA? I calculated. IA is 12 and RA is 0.5. Then tell me what is answer? 240 minus 6. 240 minus 6, nothing but 234. So finally, the voltage is 440, what is the value? 474 volts. Is there? Yeah, is there. 474 volts. Yeah, what is the answer? Actually, the voltage at the time of plugging is V plus EB. What is V? The 240 volts, and EB is equals to V minus IARA. Then we can get 240 plus 234. Finally, 474 volts. This is 100% correct answer. This is the first question in linked answer. Right, this is the second question in that linked answer. Now what they are asking, the external resistance to be added in armature circuit, the external resistance to be added in armature circuit to limit the armature current to 125% of its rated value. What is my armature current rated value? My armature current rated value 12 amperes. We calculated already. But after plugging, this armature current nothing but IAB is 125% of rated value. How we can recognize? 125%. 125% of rated value. Then its value, if you calculate it, we can get 15 amperes. If you calculate it, we can get 15 amperes. 25 fours are 25 fives are 4 ones, 4 threes are 5 threes are 15 amperes. Yeah, now this IAB they given 15 amperes. This IAB they given 15 amperes. This IAB 15 amperes, and this armature resistance we know that already 0.5 ohms. 0.5 ohms. And V plus EB just we calculated. V plus EB we calculated already 474 volts. Then we want extra resistance. The external resistance added. The external resistance added. We have to calculate this value. If you calculate 15 of 0.5 plus RE is equals to 474. 0.5 plus RE is equals to 474 by 15. Its value 31.6 ohms. 31.6 ohms. Then tell me the extra resistance added is equals to 31.6 minus 0.5. What is the value? 31.1 ohm. The extra resistance required to control the armature current to 125% is 31.1 ohm only. Yeah, this is the extra resistance required. Here the formula is same. What is the formula, sir? The IAB is equals to V plus EB by RA plus RE. V plus EB by RA plus RE. This is the formula. Based on that, we calculated the extra resistance required to the control armature current. Yeah, this is the question.